Hello, and welcome to Introduction to Rhino 3D. I am Carlos Acosta. The objectives of this course are to introduce Rhino 3D. This is how to sketch curves, surfaces, and create solids. Then we're going to also go over the basics of sketching with file extensions and user interface, also using command access, which is one of the main ways to work on Rhino 3D in an efficient manner. Also, we're going to talk about curves and surfaces. This is an introduction to how to create surfaces from spline curves and interpolation curves, and then how to get a solid from those surfaces. We're also going to talk about the principles of computer-aided design, CAD, that is of the splines, B-reps, or body representations, and rational B-splines, which are the basis of Rhino 3D. We're going to be talking about representing objects such as shapes and textures, planar views, and wireframes. Also, arrays of objects and space transformations such as rotation, mirror, translation, scaling, etc. We're going to talk about Boolean operations and surface and solids. This is union, subtraction, merging, and splitting. We're also going to go over Rhino 3D features for architecture and engineering. This is simulating physical forces and deformations, exporting to other CADs such as ANSYS or COMSOL or Abacus. We're going to go over details about rendering objects. And at the end, we're going to talk about special problems such as structures, say a bridge, how to analyze it, and how to perform a fluid dynamics simulation on a pipe or something along those lines. So this course was designed for students that have never used Rhino before, but they are familiar with other modern modeling software such as Pro Engineer or SolidWorks or AutoCAD. It's also was designed keeping in mind that some students have never used any modeling software, and that is 100% okay because there's going to be a small section about the basics of modeling. Then a third audience will be students with experience using Rhino and other software for modeling, but want to learn how to output files for 3D printing or manufacturing or analysis on final element method or computed fluid dynamics, and how to prepare the body or the object for those types of analysis. So let's start by asking, what is CAD-CAM? CAD-CAM stands for Computer-Aided Design, that's CAD, and Computer-Aided Manufacturing, CAM. So some of the most common CAD-CAM software in architecture and engineering are AutoCAD, will be a pretty common one, Autodesk, Blender, Brazil. Rhino actually can install plugins or applications to connect with Brazil. Another very common one is Mechanical Desktop, Pro-E, Revit, of course Rhino, Solid Edge, SolidWorks, and I think those are the most common ones, at least in my experience. But this is a list of all the software out there, or some of them at least. So for those of you who have never used any modeling drafting software before, never used Pro E, SolidWorks, nor Autodesk, the very first thing you have to know is that CAD softwares are usually, which Rhino is the case, are usually based on parametric curves and surfaces. That means that if you have a point in space, that point has coordinates x, y, and z. One single point has coordinates in x, y, and z. But a parametric curve takes advantage of those coordinates to create a mapping into a set of coordinates which are orthogonal, u and w. Sometimes they're also called u and v, which take x, y, and z and generate a point in terms of u and w, which that means is that you have your x, your y, and z, but the point from the real world in x, y, and z will translate into a mapping at u and w or u and v, depending on notation that you follow. So for instance, a curve, this curve, has points pm naught, pm1, all the way to pmn-1, pmn. A family of curves form a surface. So a point on that surface can be expressed as u, v, or w in x, or u, w in y, u, w in z. So notice that at this p, which is a function, you input your u and your v from this coordinate system, and it maps to real world right here. So this is a very convenient, elegant, and powerful method, because if you remember, in calculus or algebra, you would plot an ellipse as x minus h squared divided by a squared, where a is this length, and y minus k squared divided by b squared, and b is this length, and h comma k are the origin. Instead of creating this function and computing this squared and this squared, and then dividing this plus that squared, dividing that equals to 1, which has to hold this condition to be an ellipse. So right there you have subtraction, power, division, the power. You have a bunch of operations. Then versus in your parametric function, you have this elegant and short form to generate the ellipse. So you have your Rx, which is A, or the length on this axis, times cosine, which is a trigonometric function of u divided by 2 pi. It can't get simpler than this. And then for y, you get Ry, which is that length right here, times sine of u divided by 2 pi. So notice that you have this versus that. This is your parametric function to generate an ellipse. This is your standard Cartesian coordinate system function to generate the ellipse. So parametric, Cartesian. So Rhino 3D has been extensively used in architecture and engineering due to the powerful scheme of functions and powerful set of operations that can be performed to generate surfaces and solids. Now, at this point, I want to clarify that I do not aim to teach architecture through Rhino, and I don't aim to teach engineering through Rhino 3D. On the other hand, I aim to teach or introduce Rhino using examples in engineering and also some examples in architecture. Now, for the engineering side, I feel that I'll have easier time because I have my bachelor's, master's, and PhD in engineering. But for the architecture side, I hope that I get to listen to your feedback and hear corrections or even learn, because architecture, I know that in architecture you have to take into considerations both sides, the science and the art. So after saying that, we'll carry on to say that Rhino 3D has significant usefulness in architecture because you can start using your planar tools to design your plans, your blueprints, your drawings, but you can expand to much more powerful concepts such as binary objects, large objects in architecture that would be challenging to design without a computer, and that definitely take very big effort to build. So for example, we have this Guggenheim Museum in Bilbao, Spain, which again, I'm not an architect, but I simply want to say that you can see how this has the texture and the shape that is very natural for creation of surfaces. I do wish that I understood more about architecture to be able to discuss more details. Hopefully, I'll hear from you so you can teach me. Now, for this concert hall in Newcastle, UK, um, I wanted to talk about this one because I can right away see in Rhino, at least from a modeling perspective, I can see how to generate this object with an axis and then a revolution around the axis, creating a shape here. So if you were to revolve this, and we'll go through this when we open Rhino and get to revolutions. When you create an axis and you revolve this part, you can create that shape very close, very close to this shape. Of course, you would later go and pick some points and adjust them and so on and so forth. But from the Rhino perspective, is not very difficult to build. Now, from manufacturing and the real world construction, is probably very tough. But for now, I can say that from using Rhino, this building is easy to build. I do not know without Rhino how would you be able to declare those surfaces right here, those transitions from there to there, or to here, from here to here. So I don't know. In Rhino, this is very simple. We'll get to this example when we go to revolutions. Oh, this is another good example about architecture using CAD, and at least Rhino will help you do this kind of stuff very easily. This one is in Australia, the art museum in Austria. I'm sorry, not Australia, but Austria, Europe. And again, very interesting how you generate a pattern from a body and then you add some extrusions to it with a mirror, not with a mirror, but with a pattern that will have some pattern on the surface. And it's interesting how even you can see on the texture that they try to keep either here, both here and here, they keep the lines from the parametric curves. You see the texture, those lines are there. So same here. You can see the lines that form the parametric curve are still there, letting you know that this indeed is meant to be a surface. There's another example. This one is in Chicago. I like this one because stacking planes is basically you perform an operation that on the plane to get this shape right here. So I'm analyzing all this structures from how to build them from Rhino. I am truly ashamed that I don't have knowledge from an architecture point of view to be able to talk about this window setup here versus what it means to have those openings there. I'm not sure, I'm truly ashamed that I cannot get into that detail. Okay, so Rhino engineering is also very useful. In fact, this is one of the examples from the website. You can create your model and then analyze the deformation, the strain, stress, fracture, fatigue. Of course, for this, you have your knowledge in engineering. You'll know that you can get your deformations and then compute your stresses, your sigma in X, Y, and Z, or your von Mises, and then be able to compute your fracture probably through some analysis of your loads or your time domain, get into studying your fatigue. But the point is that you can study your physics from a model that you generate from Rhino or other CAD. But Rhino is very good at generating this type of geometry that is not symmetrical. More examples about how to generate machines from Rhino. One very nice thing about Rhino is that it's meant for rendering, which I don't know if we're gonna be able to go in detail because it's not part of an introduction to Rhino. So, but there are plenty of tutorials and plenty of information out there on how to render. Mostly because for rendering, you sometimes use extra packages such as Flamengo or even Brazil. So, but even the Rhino 3D rendering will do some rendering, and you'll notice how even the basic rendering is very nice. So again, you can create your geometry to perform your temperature heat transfer analysis. So you have temperatures at the inlets and outlets, so thermal insulation analysis, enthalpy, entropy, etc. So of course, I'm hoping that you realize by now that for your physical analysis, you need three things. One is your geometry. The geometry part is what I'm going to be focusing on Rhino. If you're going to be 3D printing, or if it's something that you're going to be molding because it's made by plastic or made with plastic, or if it's something that you're going to be using a lathe or a mill. But on the other hand, if it's not something that you're manufacturing, but if it's something that for now you need to design, so since there's a couple of iterations before you get to manufacturing, you need to study the stress or the heat transfer through the part. Well, those are the kind of things that you will be able to do from your geometry design. Two is your material selection. So of course, if it's stainless steel versus if it's aluminum, or versus if you're gonna use carbon steel, or if it's plastic, or if it's copper, right? So those all have different mechanical and electrical and physical properties. Now, that's the first one is geometry. The second one is the material that you choose, and the third one is the equations that characterize your system. So for instance, if it's an exhaust, your equations are going to be fluid flow coming in and fluid flow going out, temperature on the domain. Since it's gas, probably you're not going to be interested. Perhaps you don't really care about the stress on the wall because you know that the gas is not going to be close. The pressure inside is nowhere near the yield strength of your structural materials yield strength. So this is where you choose or you study the physics of your design. So there's going to be a very small part of where we're going to go through material and equations. Really what we're going to be focusing is how to generate the geometry. And then later on, you're gonna use that geometry for designing structures or for designing vehicles or airplanes or whatever you decide to use. Another example is this one is from the Rhino 3D website. So this is a good example on how to create a very nice model for a nice render using Rhino, and perhaps using the same concept to study your CFD. CFD is computational fluid dynamics. So you can study the turbulence that generates the car, and that's important because you can study the drag and the lift coefficients, CF and CF coefficients. So and the pressures on the pressure field on the surfaces to know if you're able to efficiently move without getting too much resistance from the air. Rhino 3D is also useful for art projects. So the same way that you have Rhino for designing the exteriors or interiors of buildings or houses, there's the capability of getting Rhino 3D to generate art in sculptures, for instance. So this is the introduction to what you would be probably able to get to build to use in your architecture classes or projects and in your engineering classes and projects. And even though I don't think that we don't have any art students, this is only to let you know that when you're designing, you can also keep in mind that you can have that artistic side of your design open and implement ideas with Rhino, because you can modify the surfaces without having to change too many steps